Simple harmonic motion you saw on Friday we defined as a motion in which the restoring force is proportional to the displacement. What do we really mean by that? For example, you got a spring that's just sitting there. We say it's at its equilibrium position or its natural position. It's not stretched, it's not compressed at all. Now, when I stretch that spring, when I pull that spring out like this, it requires a force. The more I stretch it out, the bigger the displacement, right? The bigger the value of x, the further it is away from the equilibrium position, then the bigger the force I need to pull it out with. That means the bigger the force it pulls back on my hand with. The force that it pulls back on my hand with is called the restoring force. If the restoring force is bigger because the displacement is bigger, the amount of stretching or squishing, then that means we have simple harmonic motion. We did this earlier, right? When we did energy and we talked about elastic potential energy, we said F is equal to kx. We learned about Hooke's law. F is equal to kx. That equation showed us that when x is bigger, F is bigger. Okay? Hooke's law describes perfectly simple harmonic motion. Here we're not talking about the applied force, though. The force that I pull with is bigger than the displacement. We're talking about the force that it pulls back with is bigger as the displacement gets bigger. But in the end, the force that I pull with is going to be the same as the force that the spring pulls back with. So, motion in which the restoring force is proportional to the displacement. In other words, everything that we did back in our energy unit involving Hooke's law, F is equal to kx, is simple harmonic motion. Now, what does that manifest itself in? Where do we see simple harmonic motion? How do we know, just by looking at something, whether it's motion in which the restoring force is proportional to the displacement, without taking a measurement of force or a measurement of displacement or so on? Well, if the motion repeats itself, it's likely to be simple harmonic motion. Because the restoring force gets bigger as I stretch it more, let's say I let it go. Okay, it's going to vibrate back and forth, back and forth, back and forth. Why is it going to do that? Because the force, the restoring force, pulls it back to where it came from, its natural position. It keeps going through its natural position, stretches more on the other side, gets pulled back to its natural position, keeps going, stretches, gets pulled back to its equilibrium position, stretches the other side, and so on. It keeps repeating itself because the restoring force is proportional to the displacement. This is how we know it's simple harmonic motion. This is our everyday definition of simple harmonic motion, motion that repeats itself. This is our more scientific or technical definition of simple harmonic motion. We talked about some examples on Friday as well. Clearly the spring, okay, a spring or an elastic is an example of simple harmonic motion. Either one of those. Stretch a spring, let it go. Stretch an elastic, let it go. But we also talked about another one, the pendulum. It is an example of simple harmonic motion. The pendulum is that object, that device that has a string, and we call it a bob on the end of it. A bob is hanging from a string. And his bob is swinging back and forth, back and forth, back and forth. You're getting sleepy, getting very sleepy. As the pendulum bob swings back and forth, it's difficult to measure this, but if you could measure the restoring force, the force that's pulling it back to here, which is its natural position, its equilibrium position, if you were able to measure the restoring force, it would be bigger and bigger and bigger and bigger as the displacement gets bigger and bigger and bigger and bigger. Motion in which the restoring force is proportional to the displacement, that's simple harmonic motion. So the pendulum is an example of simple harmonic motion. How do we see that? Well, because the motion of the pendulum repeats itself, back and forth, just like the spring does. Yep. Yeah, I think so. Yeah. We talked about two more terms, two terms that aren't new, but were new to us in the context of simple harmonic motion. Frequency and period. Frequency, if you remember from our circular motion unit, was the number of revolutions per second, or in this case, we just simply say the number of cycles per unit time. How many times the spring vibrates back and forth, back and forth, back and forth per second, or how many times the pendulum swings back and forth per second. back and forth, back and forth, back and forth per second. The number of cycles per unit time. And the equation for frequency is going to be the same as it was in our last unit. It's simply going to be the number of cycles over the total time. Now, this equation is important, but it's not on your data sheet because it's really just a definition, right? The period, it's the exact opposite, literally the inverse of it. It's the time per cycle. So instead of being F is equal to cycles over time, it's going to be T, big T, is equal to time over the number of cycles. How are you going to tie those two equations together? How are you going to relate them to each other? Well, this isn't new either. Back in our circular motion unit, we said T is equal to 1 over F. This equation is on our data sheet. Okay, the period is equal to the inverse of the frequency. Now, we've spent some time back in our energy unit on a spring vibrating back and forth, simple harmonic motion of the spring, Hooke's law, F is equal to kx, and the energy involved in that spring. Today we're going to spend a little bit more time on the pendulum, which is the last, literally, the last topic that you have to be familiar with for your field trip on Friday. A pendulum, we said just a minute ago when we were talking about it as an example, we said essentially it's a device that consists of a string and an object that hangs on the end of that string. We call it a bob that swings back and forth. A grandfather clock, the keys on the end of the string going back and forth, back and forth. And the period of a pendulum is the time, of course, that it takes for one complete cycle. But the time for one complete cycle, we've got to remember, is measured from starting position back to that same starting position. A lot of people will do this. Okay, a lot of people will look at the pendulum and say, okay, start, that's one complete cycle. But it's not. That's a half a cycle. That's not repeating itself. Okay, it's halfway through repeating itself. You got to go back to the starting position. So it's the time that it takes the pendulum bob to move from one spot through a complete cycle back to where it started. The equation for a pendulum, for the period of a pendulum. T is equal to what? We're going to do a little activity here. Not a hand-in thing, not a write-up thing, just a quick little activity to try to help us to determine some of the variables that affect the period of the pendulum. Okay, what I want you to do is this. Come up with something. Come up with an idea that you think might affect the period of a pendulum. Okay, what influences how long it takes the pendulum to go back and forth, back and forth? We'll come up with a list of a few things, and then we'll test them. Part of the room will test one thing, part of the room will test another thing, part of the room will test another thing, and we'll see what actually does affect the period of a pendulum, and then we'll come up with the equation from that. Tell me one thing that you think might affect the period of a pendulum. Okay, the length of the string. I'm writing down whatever you tell me here, guys. I may paraphrase. If I find a couple of things are pretty much the same as each other, I may combine them. But in the end, okay, whether it's true or it isn't, I'm writing it down. Nathan? Okay, so let's say the initial position. Anything else? The mass of the bob. Anything else? Yeah. Okay, gravity. Let's say the gravitational field, because in the end, the force of gravity would be dependent upon the mass and the gravitational field. We've already got a mass that we're going to test here. So let's say the value of g. Now, unfortunately, we're not going to be able to test for that, right? Because we can't go somewhere else to test for that. Can test for the other ones. Anything else? Some people at this point will usually say the angle, the initial angle, but that's kind of related to the initial position, right? If the angle is bigger, the position is bigger. So if we test position, we're going to test the angle as well. Good? Okay, I'll tell you right now that G matters. The gravitational field matters. If it's not 9.81, the period of a pendulum is different. Okay, a grandfather clock on the moon would not work the same as a grandfather clock on Earth. It wouldn't be even close to being calibrated. In fact, a grandfather clock in Vancouver wouldn't even keep the same time as a grandfather clock in Calgary because the gravitational field is different. Now, it wouldn't be dramatic because the field strength isn't dramatically different between Vancouver and Calgary, but it would be different. Gravity matters. Gravity affects the period of a pendulum. But what about the other three things? Okay, I would like this third of the room, okay, right here, row 1 and row 2, to test the length of the string. Come up with a way. Okay, you can work in a couple of different groups if you want. You guys figure it out. Come up with a way to test for the length of the string, and then do it, and see if the length of the string matters. Okay, you guys are going to determine, or going to test the initial position of the pendulum. You can think of it as the angle if you want. Okay, that might be an easier way to think of it. Okay, the initial angle. Okay, 0 degrees, 10 degrees, 45 degrees, so on. Okay, that's going to be your job. You can split up into a couple groups if you want. That's completely up to you guys. And let's go, you three, actually, let's go over here because you guys are, there's not very many of you and there's not very many of them. So you guys are going to test the initial position as well. You guys are all going to test the mass. Maybe split up into 2 or 3 groups, whatever you want to do. Okay, just come up with results for me. Okay, write down some results, but don't hand anything in. I just want to know at the end of this whether this matters, whether this matters, and whether this matters. All right, we're all finished, guys. We've tested 3 different factors. Length of the strength, length of the strength, did I say? Length of the string, it should say. The initial position and the mass of the bob. These 2 rows tested the length of the string. What did you guys find? Does it matter? It does. Yeah, it does. You're right. We'll do a quick little thing here, just an anecdotal thing here. No numbers, but the rest of you will see that the length of the string matters as well. Okay, I'm going to pull this back to about 45 degrees. Okay, and I'm going to pull it back to about 45 degrees each time. Okay, first time the length of the string is however long this lanyard is. Okay, it's, I don't know, 45 centimeters maybe, 40 centimeters. Okay, pull it back, let it go. I'm going to say start and stop. Start when I let it go, stop when it comes back to its initial position. So that's going to be the time for 1 complete cycle. In your mind, you're going to kind of time it, not with a stopwatch, but you'll know, right? If I say start, stop, that's about the same, right? If I say start, stop, well then clearly that's 2 different periods, right? Okay, so listen carefully, kind of try to time it in your mind and see if the length of the string matters. Okay, 45 degrees, 40 centimeters, let it go, start, stop, start, stop, start, stop. Okay, now let's change the length of it. Let's decrease the length of it. Same angle, start, stop, start, stop, start, stop. Did the length of the string matter? Yeah, when I made it shorter, then the period decreased dramatically, so much so that I could tell that it was a smaller period even without timing it. So the length of the string definitely mattered. Let's look at initial position. What did you guys find in the middle 2 rows here? Did the angle matter? The initial position matter? Yes? Okay, let's try it. You guys say it did? Do you guys agree with that? Okay, let's start it at a small angle. Maybe, I don't know what this is, maybe 10 degrees. Okay, start, stop, start, stop, start, stop. Okay, let's increase it a little bit. You see that it's higher here, right? Start, stop, start, stop, start, stop. Does that sound like any different? Kind of sounded the same. Well, let's increase it a little bit more just to make sure. Start, stop, start, stop. Start, stop. Down to a smaller value again. Start, stop. Start, stop. Isn't it pretty much the same? Watch what happens when I increase it to a big value, though. Start, stop. Start, stop. That was a higher period, wasn't it? Here's the thing. At small angles, the angle doesn't matter. it's an approximation. The angle always matters, but at small angles it matters so little that it's never going to matter. So you're dealing with a small angle of 10, 15, 20 degrees. The angle is irrelevant. And that's what we'll be dealing with, is angles 5, 10, 15, 20, 25 degrees. Basically, the rule of thumb is this. If you're below about 40 degrees, okay, you're good to go. The initial position or the angle isn't going to matter. Okay? You guys were right. Okay, whatever you guys came up with, the fact that the initial angle mattered is technically right. Okay, but at smaller angles below about 40 degrees, it matters so little that it's not going to matter for us. Okay, got it? Now, quick little question for you here, just as a little aside. Even though that initial position doesn't matter, can anybody explain to me why it doesn't matter? How can it possibly be the same period, pretty much the same period, when I drop it from here versus dropping it from here? Start, stop. Start, stop. When it has further to go, why does it not take longer? Force of gravity is the same. Oh, it contains a higher velocity? The bob, you mean? Goes higher velocity? Okay. Yeah, okay. So we'll kind of tie those two together there, those two answers together. When you put it at a higher angle, it has further to go, right? But watch the speed. When you put it at a higher angle, here's the low angle. Start, stop. Start, stop. Put it at a higher angle, watch the speed. Okay, further to go, more distance, but watch the speed. Start, stop. Took the same time, but it was going faster, right? It has further to accelerate. So basically, when it goes a small distance, it goes slow. When it goes a big distance, it goes fast. And those two balance out to give you about the same amount of time. That is, unless you're dealing with an angle that's 60, 70, 80 degrees. And then it's a noticeable difference in time. So again, for small angles, we're going to say that it doesn't matter. What about the mass of the pendulum bob? What did you guys find? Didn't matter? Okay. Why doesn't it matter? You're right, by the way, it does not matter. Okay. I can put a set of keys on here. Okay. Start, stop. Start, stop. Or I can attach something like, well, I don't know if I dare do this. Give this a whirl here. Guys, do you still have the start, stop in your head right now? Okay, you ready? Start, stop. Start, stop. Was that the same? Pretty much the same, right? The mass of the pendulum does not matter. But why not? Shouldn't the heavier one go faster than the lighter one? Yeah, it's like drop something, right? Drop a feather, drop a hammer. If there's no air resistance, they're both going to accelerate at the same rate, right? And what's feeding this? Like, what's causing it to fall? It's gravity, right? Gravity is not affected, the acceleration due to gravity, that is not affected by the mass of the experiencer, only the mass of the producer. So the mass of the bob doesn't matter. So what are we saying? The only thing that matters is the length of the string? Yeah. And the gravitational field strength, right? 9.81 or 9.78, whatever it happens to be. Here's the period of a pendulum. It's the equation you've been waiting for. Not really. 2 pi square root L over G. The reason you have not been waiting for this is because it's kind of a pain in the butt to rearrange to solve for L or G. We got to be able to do that. Before we do it, let's identify what these variables are. L is the length of the pendulum, and it's going to be in meters. G is the gravitational field strength, or the acceleration due to gravity. And that's going to be in meters per second squared, or you could say newtons per kilogram. Either one of those works just fine. Solving for T in seconds, that's easy. Solving for L or G, maybe not so easy. Let's go through the rearranging of that equation right now. I want to solve for L. What do you want to get rid of first? Yep. 2 pi. So let's take it over by dividing. T over 2 pi equals the square root of L over G. So far, so good. We're still a ways from solving for L, though. What's next? Joseph? Square both sides. So it becomes T over 2 pi squared equals L over G. We're getting there. Okay, we're getting there. We want to solve for L here. What do you get rid of next? There's only one more thing to get rid of, right? It's G. So how do we take that over to the other side? Multiplication, right? So it becomes G times T over 2 pi squared equals L. The red one is the form that appears on our data sheet, but the blue one is same equation solving for L, the length of the pendulum. Can you guys do that? Okay, what about solving for G? This one's even worse. Boy, wait till you see the final product. It looks ugly. Yeah. Yeah. Hey, what if I did this? What if I said G times X is equal to L? When I asked you to solve for G, what would you do? If I asked you to solve for G, what would you do? Yep. No, hold on. This one. Solving for G. Divide by X. So it would be L over X. All we're saying there, right, Julia, is that X is T over 2 pi squared. So it becomes G equals L over X, or L over T over 2 pi squared. That looks really ugly, right? Looks really ugly. But it's right. We'll square that one off in blue as well. Again, red on your data sheet in that form. Blue, it's on your data sheet, but not rearranged like it is right here. Good. Be able to rearrange both of those. Here's why. Some of you might say, you know what, I'm gonna memorize this. I'm gonna remember the form of this. Okay, listen, it's May the 25th. You have your final exam in about a month. I can't remember the exact date. If you memorize this today, what do you think the odds of you having that still in your memory in another month are? Slim to none, right? Slim to none. Okay, what do you think the odds of you remembering how to rearrange it are? Probably pretty good. If you can rearrange it now, you'll probably be able to rearrange it later. Okay, so invest the time now, learn how to rearrange it, and then you should be good later on. All right, let's take a look at an example. Notice we're in chapter 7 now. 7.8, 379 says, what's the gravitational field strength at the top of Mount Everest at an altitude of 8954 meters if the pendulum with a length of 1 meter has a period of 2.01 seconds? What are we going to do here, guys? We're going to say the period is 2.01 seconds. We're going to say the length of the pendulum, 1.00 meters. Do we need the altitude of Mount Everest here? Do we need that number? No, we don't, do we? If we're solving for a gravitational field strength, using the producer equation, G is equal to Gm over r squared, then we would need the altitude of Mount Everest, and in addition to that, the radius of the Earth. So we'd add the two together. Okay, that's not the way we're trying to solve this question. We're going to solve this question using the pendulum equation, T 2 pi square root L over G. But we're solving for G. It's the ugly one. 2 pi goes over by dividing. Square root goes over by squaring. G goes over by multiplying. And T over 2 pi squared goes over by dividing. Let's plug our numbers in here. L, 1.00 meters. t at 2.01 seconds. Hey, I could see a great question just like this, except they don't give you the period, they give you the number of cycles, and they give you the time. You could find the period by dividing the time by the cycles, right? 2 pi squared. Let's do this on the calculator, because got a feeling you might mess up on this. Okay, what do we got here? Let's do the bottom first. Let's say 2 times pi. 6.28319. Let's say 2.01 divided by that. 0.3199. That's the bottom, right? Before we go any further, what's your prediction? Before we go any further, what's your prediction here? What do you think it's going to be? 9.77 is your prediction, cheaters? What do you get when we actually go to calculated, cheaters? Whoa, look at that, 9.77 newtons per kilogram or meters per second squared. So, and we talk about it as being like 9.81-ish, you know, in sea level, Calgary, okay? 9.77 isn't going down very much, is it? But it's measurable, right? It's going down a measurable value. Let's see what you can do with these 3 questions, please. Okay, remember, question number 3, funny enough, question number 3, the easiest of the 3 they put last. Okay, the other ones, you got to rearrange. You got to rearrange to solve for G. You got to rearrange to solve for L. Let's see what we can do with those. All right, finish those up for homework if you haven't finished them already. I want to take a look at one more little concept that's related to what we've been doing. Obviously, it's called resonance. I'm going to describe what it is first, and then we'll give you a ton of examples involving resonance. The first part of the explanation as to what resonance is depends upon another definition for resonant frequency. Resonant frequency is a natural frequency of something, a natural frequency at which something wants to vibrate. Okay, if I hit the desk right now with my fist, you hear a sound. I'm causing the desk to vibrate at its natural or resonant frequency. It has a unique sound, a characteristic sound. Every time I hit that desk, it will produce the same pitch. Why? Because the resonant frequency, the natural frequency of the desk, matches with that sound. Now, if I take a meter stick and I put the meter stick over the edge of the desk and I fling the meter stick, okay, you're going to see that it's going to vibrate back and forth at a particular frequency. That's the resonant frequency of the meter stick. Watch what happens if I shorten the meter stick. Did it change? Yeah, it's like a guitar string, right? When you have a finger on a fret of a guitar, it has a certain natural frequency at which it wants to vibrate. When you put your finger on a fret, on a different fret, it vibrates at a different frequency. Put your finger on a, what do they call them in horns, like valves? A horn, okay, it produces a different pitch, right? Because it produces a different resonant frequency, a different natural frequency of that instrument. Everything has a natural or resonant frequency. Everything, okay, everything, including you. Now, you tend not to vibrate at that natural or resonant frequency, largely because your resonant frequency changes so easily, right? All I had to do with the meter stick was change the length of the meter stick. All you got to do to change your resonant frequency is breathe, because now you're a different density, or move an arm, or a million different things you could do to change your resonant frequency. Everything has a natural or a resonant frequency, though. I'm going to define this as the natural frequency at which something wants to vibrate. And it doesn't take anything crazy, anything technological, anything monumental to cause something to vibrate at its natural frequency. Okay, Terry's desk just vibrated at its natural frequency because I knocked on the desk. Okay, the meter stick just vibrates at its natural frequency because I just flicked the end of it. A wine glass vibrates at its natural frequency because you rub your finger around the edge of the wine glass. A water bottle vibrates at its natural frequency when I blow across the top of it. Put some water in there, what happens, by the way? The pitch changes, right? Because the resonant frequency, the natural frequency changes when I put water in there. Everything has a natural frequency at which it wants to vibrate, and it doesn't take much to get it vibrating at the natural frequency. That's not resonance. Resonance involves applying a force. Repeatedly. At the resonant frequency of the object. So what does that do? Well, if I flick the meter stick and it vibrates back and forth like this, I can't apply a force at that frequency. Not myself, anyways. I can't do it quick enough. The pitch of that you heard, the vibration of that, the number of cycles per second that underwent, I can't possibly push on that meter stick at that rate. It's too quick. But there's sometimes when I can. Let's say a swing set. You guys have done this a million times, right? Everybody's done this when they're kids. Swing set's going back and forth. You want to cause somebody to go higher on the swing set, what do? You push, right? You push them. But you don't push them at random frequencies, like this, because that's chaotic. When do you push them? When do you push them? Answer this question. When do you push them? At a very specific time. What's it called? You push them at the resonant frequency of the swing. This is the frequency at which it wants to vibrate. If you push them at that frequency, then what happens? They go higher and higher and higher. So what happens here? When you apply a force repeatedly at the resonant frequency of the object, the amplitude of the vibration grows. If you apply a force on the swing set at the right frequency, then the swing set goes higher and higher and higher. If you apply a force on the swing set at random frequencies, then the swing set doesn't go higher because you're not matching the natural frequency of the swing set. If an opera singer sings at a really high pitch that matches the natural frequency of glass, the glass starts vibrating, right? You hit the glass starts vibrating. But if you can apply a force at the natural frequency of the glass, like the opera singer is doing when she's singing, right? She's applying a force repeatedly with her voice against the glass. It causes the amplitude of vibration of the glass to get bigger and bigger and bigger until the glass breaks because it can't handle that much vibration without breaking. There was a situation 60 or 70 years ago now, I can't remember the exact date, in a place called Tacoma, Washington. There's a bridge that had been built spanning this, the Tacoma Narrows, it was called. This channel here with water down below, this river or something down below here. This bridge was a suspension bridge. Even when they were building this bridge People notice that, boy, that thing is swaying a lot. Bridges sway. Bridges move. They're supposed to move. Buildings move in the wind. Okay, if they don't move in the wind, then what's going to happen? They're going to snap off, right? Apply enough force, it doesn't vibrate. Apply enough force, it snaps off, and that's worse than vibration. Okay, a vibration of a bridge or a building might make you kind of feel sick, but it keeps you alive. When the building snaps off, that's worse than feeling a little bit sick. So people, even when they were building this bridge, noticed that, hey, look, this thing is vibrating quite a bit, actually. It's moving quite a bit in the wind. About 6 months after it was open, it's a windy day. Not like a hurricane wind or a tornado wind or whatever, nothing like that. It's just a windy day. The wind was gusting, and it's gusting at the right frequency to match the natural or the resonant frequency of this bridge. What happens? The amplitude of vibration of the bridge got bigger and bigger and bigger until at some point the bridge couldn't hold it anymore. What happened to the bridge? Just like the glass, it breaks. It falls down. And the bridge literally crumpled down.